Hello again. Juri Davash tells me that there's live streaming that's taking place and you can get on to that through the webpage. Is that correct, Juri? That's okay. So I would like to introduce now the last speaker of the morning session. And he is Professor J. Kappraff of the New Jersey Institute of Technology. He's a professor of mathematics. I've met Jay a number of times, and I was enjoying and still enjoy the second edition of a book he wrote of Connections, the geometric bridge between art and science, or science and art. It's in the second edition. And I'm going to tell you what the title of the talk is. There's a slight change in the title, one-word change. And his lecture is Proportions of the Parthenon and its Connection to a Vedic ceremonial altar and to earth measure. Measure is the additional word. So now I'm going to turn this off, and you will turn your microphone. And I'll give you...
Okay, this on? Yeah, you can hear me, yeah, great. I'll start off with a brief introduction I'll read to you to orient this work. This work has been a collaboration between Anne Balkins, who did her PhD thesis on the proportions of the Parthenon, the ethnomusicologist Ernest McLean, and myself. In 2006, I spoke at the Symmetry Festival on the Parthenon and showed how its major proportions related to the frequencies of the pentatonic musical scale. I'm now going to report on some connections between the Parthenon builders and ancient Vedic astronomy and geometry. The Vedic Indian culture is generally considered to date from about 500 BC to 1500 BC, originating from the Indo-Aryan and Harappan cultures, and a precursor of Hinduism. Vedic geometry can be found in the Sulba Sutra, a book published between 500 and 800 BC. This may have been the first book of geometry that was written down, although it was based on material that was known as far back as 2000 BC in the Harappan culture, and perhaps even longer. Sulba stands for rope, and the Sulba Sutra presents geometric compass and straight edge constructions, using a rope as a compass, and then applies this to the construction of ceremonial altars made of precisely baked bricks. There appears to be a direct connection between Vedic India and classical Greece. Many ceremonial altars can also be found in Greece. Similar connections can be found in the geometry originating in Egypt, China, and Iran. We do not know if Vedic India was the origin of this geometry, or if there was a common source for all of this work. I can say that Vedic astronomy was quite advanced, and they appear to have computed the length of the solar and lunar years with perfect exactness. And Anne Balkins has found these numbers for the solar and lunar year and encoded in the proportions of the Parthenon with equal exactness, as I will show. The solar and lunar years are fundamentally incommensurate. However, the Greek astronomer Meton, working a few years before the construction of the Parthenon, proposed what has been called the Metonic cycle, in which 235 lunar months are almost exactly equivalent to 19 solar years. As a result, cultures that use the lunar calendar require every 19 years, 7 of these years to have 13 months. In other words, 7 intercalary months are added to the calendar each 19 years. And the Metonic cycle has been verified by Balkins' computation of solar and lunar years. My sources for Vedic India are the scholar of Vedic astronomy, Subhash Kark, the ethnomusicologist George Georgiesi Joseph, and John Price, who brought my attention to a particular fire altar called the Rathakashra City Chariot Wheel, which appears to have connections to the Parthenon. In a way, the study of proportions can be thought of as a kind of mathematical excavation, the unearthing of messages from the past fixed in stone. We'll be making use of, this is a perfect example of what is called the Greek quadrivium, which asks Greek students to keep their eyes on unity and study music, astronomy, geometry, and number. And these fit perfectly within Parthenon. The Parthenon is a Doric temple with certain Ionic features, dedicated to Athena Parthenos. It was constructed between 447 and 432 BC, which places it just between the ages of Pythagoras, whose dates are 570 to 497 BC, and Plato, who lived from 428 to 347 BC. It was built on the site of two previous Parthenons that were destroyed by the Persians, the arch enemies of the Greeks. The Parthenon sits on a platform. Oops, sorry. Yes, a platform called the stylobate, and has 8 columns to the east and 17 columns to the north and south. Unlike other temples, which had 6 columns to the east and west and 13 to the north and south. Atop of each column, there are concrete blocks called the triglyphs. And between 2 triglyphs, there was a panel called a metope, in which the sculptures were constructed by the great Greek sculptor Phidias, depicting scenes from history and mythology of Greece. These have been removed from the Parthenon and are presently sitting in the British Museum in London, where I saw them in January. They're quite impressive. I will first focus on the units that Balkans has hypothesized to reveal aspects of the temple. Then I will take you through an analysis of several snapshots of more lengthy presentations, such as the connection to the musical scale, computation of solar and lunar years in both Vedic India and in the Parthenon, use of Pythagorean triples, the analysis of the ceremonial altar called the Rathakashra City Chariot Wheel, with close connections to the Parthenon, and the use of the chariot wheel to approximate the square root of 2. Okay. This is an ambitious program which we hope to carry out now. There are 2 reasons why this analysis deserves your attention. First of all, the Parthenon, more than any other temple, was crafted to extraordinary precision. Second, Balkans has drawn on the careful measurements of the Parthenon undertaken by the architect, or archaeologist and astronomer, Francis Cranmer Penrose in 1885, before the temple began to deteriorate. This gives a measure of trust to the numbers that I will be presenting. And here is what Manolis Koros, the curator of the Parthenon, had to say about the accuracy of construction. And this is a message that he wrote to my colleague Anne Balkans. Recent observations and measurements have added much to our knowledge of the celebrated precision with which the Parthenon was constructed. For instance, the resting and bearing surfaces of the middle drums of all the columns are so perfectly flat that at no point is there a divergence from a mathematical plane of more than 1/20th of a millimeter. These surfaces are so perfectly parallel that along the perimeter of any of the drums, its height fluctuates by no more than 1/1500th of a millimeter. And wherever they have survived, the joints in the crepadoma are so hermetically sealed that they cannot be examined even when seen under a microscope with a power of 60. It's clear then, at least to those sufficiently familiar with the quality of engineering work, that even the most refined structures built in other eras, including our own, often lag far behind the constructional precision of the Parthenon. And Malula's chorus also said the following in regard to Penrose. He said, Penrose made original observations of the unique importance and produced the most refined architectural measurements of all time. It is a monument of scientific method, consistency, and unparalleled human skill, measured by Penrose to a highest level of approximation of 0.3 of a millimeter, and published in his book, The Principles of Athenian Architecture, of which there exist several copies, one in the library of the Metropolitan Museum of Art, and I've actually taken that book out several times. So, let's take a look at what we have here. That's the end of this lengthy introduction. Give you some orientation. So there's something truly unique about this structure, at least in terms of its precision. Obviously, we're trying to give some sort of message. Here is a picture of the Parthenon. There's the outer temple, which sits on the stylobate, and then there is an inner temple called the cella. The cella has two rooms. One room is called the naos, where there was a statue of Athena, no longer there, surrounded by a railing. The railing is no longer there, but the imprint of the railing can be seen on the floor and measured. The only, up until the work of Amboltons, the only proportions that were known were the ratio of length to width, 9 to 4, or height to width, also 9 to 4, or a measure between the columns to the width of the columns, 9 to 4. Or, by the way, there's a second room called the Epistodomos. Epistodomos was used as the treasury of the Delian League. Okay, numbers. Now, numbers fit very greatly in the Parthenon, and generally the numbers 4, 6, and 7 are attributed to Athena, and 9 to Poseidon. Athena and Poseidon contested to see who would be the patron of Athens, and Athena won that battle. These numbers appear all over the Parthenon. For example, the numbers, there are 46 columns along the perimeter of the temple. Inside the cella, there are 2 stories of 23 columns equaling 46. There are 4 Corinthian columns in the Epistodomos, and 6 Ionic columns at the east and west porches, 9 columns along the side of the naos, and there are 444 porphyry panels, 9,000 marble panels, etc., etc., etc. These numbers abound in the Parthenon. So I'd like to take a look at some snapshots now of make up for the remainder of this presentation. So snapshot number 1 will consist of the units that are used. And this is of crucial importance. And because of the precision at which this thing was built, these units really mean something rather than just being some aimless numbers. So every temple had a module, and a measure of a foot. In this case, the module is the width of the triglyph, and 2.5 Parthenon feet equal the length of the module. And this was these were uncovered by Anne Balkins. This is Anne Balkins' idea of the Parthenon foot. By the way, the great historian of temples, Vitruvius, also specified that the module should be the triglyph. This led the Parthenon foot to be, This led the Parthenon foot to be 343 millimeters, which turns out to be 7 times 7 times 7, interestingly enough. Of course, we might wonder what is millimeters having to do with the Parthenon back in ancient Greece. And there is an answer to that question, and possibly in future talk, we will describe this. There is a connection. The Parthenon foot then is further divided into 16 equal parts, each part called a dactyl. The dactyl is about the width of a finger joint of your finger. So this gives you some sense of human scale. With this measurement, the module turns out to be 40 dactyls, the metope 60 dactyls. And Vitruvius said they should be in a ratio of 3:2, which they are. A word about these measurements. The actual measurement of the width of the length of the stylobate is 3214.25, and we can use all these decimals because they are significant according to the. They are significant. However, there was also an interest to come up with the integers that are as near as possible to them. And the integers for the width, for the length rather, is 3240, and for the width is 1440. And these numbers are within 0.02% of their fractional values. And they will help us to tell the story. So, continuing on here, here are the measurements of the other elements of the Parthenon. The height of the the width of the cella, the width of the stylobate, the length of the cella, the length of the stylobate, and these numbers here turn out to be the relative frequencies of the pentatonic scale. And we'll take a look at that in a moment. Also, between the 4 and the 9 now appear a 6. And in other words, 24 is to 36, is 36 is to 54, is the same as 4 is to 6, is 6 is to 9. Also, it turns out that the area of a rectangle can be also equal to the area of a corresponding square. For example, let's show that here. Here the area of the cella turns out to be equal to the square, which measures the naos. And here is snapshot number 2. There's no time to talk about in length about the musical aspect of this how the numbers were obtained. They do appear in the article that's from the conference, and I did talk about this 3 years ago, or 6 years ago. But here It's all based on this cryptic diagram found in the Timaeus of Plato's Timaeus. On the right, you see a bunch of numbers, a ratio of 2. On the left, a bunch of numbers, ratio of 3. In Greek lore, 2 was a female number, and 3 was the first male number. Multiplying a relative frequency by 2 doesn't move you to a new tone. It takes you from the same tone to the same tone in a different octave. To get a new tone, you really have to multiply the frequencies by powers of 3. And that is shown better here. This is a table of a Roman mathematician by the name of Nicomachus. Lived in about 150 AD, and he understood the musical system of the Greeks. And you can see here that all these, in each column, there are integers in ratios of 3 to 2. 3 to 2 is called the musical fifth. If I start with a D, I get D, E, F, G, A. 5 tones later, I get what we call a musical fifth. And see, these are successions of musical fifths, and the musical scale can be built from them. And so the 6th column, you see the numbers that I just previously showed you for the Parthenon. So by using Anne Bulkin's unit, you get exactly the values for the pentatonic scale that Nicomachus came up with. The 7th column gives you a heptatonic scale. And the fundamental of that heptatonic scale is the D. 216. And by the way, any one of these numbers can be thought as equivalent to their doubles, or any powers of 2. So 216 can also be thought of as 432, or 864. And these will come up, actually, in the Parthenon. So let's take a look. By the way, I'll just point out something about the 4th column. Musical fifths abound not just in music, but they occur in many other places. For example, the moons of Jupiter and Saturn appear to be spaced according to musical fifths. Also, I discovered recently, working with Sergei Petukov, as a matter of fact, the talk I gave in the last Symmetry Festival was about row number 4. And these correspond to the number of hydrogen bonds in the amino acids, and led to the following diagram. This was a quilt padding that I had someone constructed for me, and these are the hydrogen atoms, hydrogen bonds, the amino acids. So all musical fifths. Snapshot number 3 are Pythagorean triples. Now, Pythagorean triples were well known. Actually, they appeared on a cuneiform tablet called Plimpton 322. Back in as far back as 1500 BC. And here are the first 3 Pythagorean triples. 3, 4, 5 triangle, where the sum of the squares equal to hypotenuse. And I'll point out that the radius I'm talking about here is the radius of the inscribed circle. The second one has a radius of 2, and that's the 5, 12, 13 right triangle. And this one, 8, 15, 17, is a very interesting one, and that turns out to appear in that ceremonial altar, which I'll get to shortly. And that had a radius of 3. So let's take a look at 3, 4, 5. Turns out that there are 6 3, 4, 5 triangles that tile the stylobate. Interestingly enough, the areas turn out to be equal to 777600. Those are Athena's numbers. 1080 is another very important number, which we'll see. The radius of the inscribed circle turns out to be 360 dactyls. Now, 360 had connotations in Greek culture and also Indian culture. In Greek culture, it was called the length of the canonical year, a perfect compromise between the length of the solar year, 354, and the lunar year, 354, and the solar year, 365. In Indian culture, 360 turned out to be exactly the length of the lunar year, but not measured in days, measured in a unit called tithis. Tithis is a little bit longer than a day. And here is a picture of how they look. In the stylobate, you see the 6, 3, 4, 5 triangles tiling it with a inscribed circle. Okay. You notice the cella has an area of 432 and an area of the Deus 864. Those were the fundamental tones for the heptatonic scale. So they appear right here, musically. By the way, if 360 is taken to be the unit, in other words, every dimension is multiplied by 360, then you actually see not just a 9-to-4 ratio, but you actually see units of 9-to-4. The 5, 12, 13 triangle in the cella, well, you notice the area is 6,000 exactly. The perimeter is exactly 6,000. And the inscribed circle has a radius of 400 dactyls. Perfect numbers again for Athena. And here's how it looks. You take the distance between the columns, 1, 2, 3, 4, 5, and then this turns out to be 12. You get the 5, 12, 13 triangle in the cella. Okay, snapshot number 4. Vedic Indian measure. So we've been mostly up to now talking about Greek measure. Some of you may be familiar with this picture. It's called Modular Man. Is there any problem with feedback?
A little bit to the left.
Okay. Hello? Yes. This is Modular Man. This is the modula of the 20th century architect Le Corbusier, where his modular system was based on a 6-foot traffic cop with his hands held over his head. He gave the first 2 starting measurements for the creation of his modular series or architecture. What does this have to do with anything that we're talking about? Well, it turned out that in Vedic Indian measure, a 6-foot man with his hand over his head was measured to be what is called a Purusha. And there were 120 angulas equals 1 Purusha. And the angula and Yes. And 8 dactyls equal 9 angular. So the angular is almost like the dactyl, a little bit smaller than a dactyl. And all of the fire altars, ceremonial fire altars in India, ancient India, were 7.5 square purushas, every one of them. And if I write them in terms of angulars, it turns out to be 108,000 square angulars. This number is one of the most sacred numbers within ancient Vedic culture. And by the way, if I multiply this by 4, any number can be multiplied by a power of 2. If I multiply by 4, I get 432,000, which turned out to be the number of syllables in the Rig Veda, which was the ceremonial book of Vedic India. And also 108. Let's take a look at number 108. Yeah, there are 108 moon diameters is the distance from the Earth to the moon. Very close. Not exact, but very close. There are 108 sun diameters is the distance from the Earth to the sun, which is the reason why the sun and the moon look to be about the same size. Also, 108 come up all over the place, even in our own times. The number of rosary beads are exactly 108. The Jewish symbol is 18. And Angkor Wat, was surrounded by a moat, 5 great roads leading from 5 gates. On each road were bordered by 108 huge stone figures. So this number, here is an idea of Anne Bolton, which I believe is very interesting. If you look at 1440, which is the width of the stylobate, that turns out also to be exactly the number of minutes in a day. Now, if I broke a day into 120 times 120 parts, each part would then measure exactly 6 seconds. And 120 times 120 would correspond to an area of 120 by 120 would correspond to 1 day. So we can change area into time, into what I call Parthenon day units. So for example, the area of the stylobate is this. If I divide it by 120 times 120, I turn it into 324 days. Now, what about 324 days? So we must take a look at snapshot number 5, which is the solar and lunar year in both Vedic and Greek systems. Here it is in Vedic Indian measure of the solar year. There are 27 what is known as nakshatras per month, or 324 days, but not days exactly. They're called tithis, slightly longer than a day. There was then a correction. Sorry about that. There was then a correction factor of 48 tithis. So 324 plus 48 is 372. Then there was an elaborate construction of altars added on each year for a period of 95 years. By the way, 95 is an interesting number. It's 5 times 19. 19 years is the metonic cycle. So at the end of 95 years, they would subtract 90 days. subtract 3 months. And they ended up with a figure, with a value which turns out to be exactly 365.24 days, which is almost exactly what we have found in our more modern times. And this was apparently unknown back in ancient Vedic India. Well, it also appears in the Parthenon. Because if I now use 120, now it turns out that there are two very important numbers that come up as part of this study. One of the numbers is 120. Remember, there are 120 angulas in the Purusha. And here, if we use that as a unit, then the width, the length of the Parthenon is 27, the width is 12. Exactly, and the area in time units, and Parthenon day units, turns out to be 324 for the whole thing, not just for the middle panel, but for the whole thing. Interestingly enough, in the cella, the 48 occurs. So an area is taken in the cella to be added to the area in the stylobate. What's missing here is 90 over 95. And so this does not recapitulate the exact value of the solar year, but it begins to show how to construct it. Take an area of the stylobate and add some area from the cellar. And this is what Anne Wilkins did very recently. First of all, took the stylobate, measured it in Parthenon day units, but did it much more accurately by using these fractional values, which are still significant. And she came up with, this number right here. And these figures are significant. And here is a picture of, so that was for the stylobate. This is for the cellar. She took this area here, right, hugging the colonnade and the nails, right to the entrance of the nails, and she measured the length and width and came up with her first measurement. 40.84 days using Parthenon day units. And it was based on the colonnade surrounding the statue of Athena, right to the length, entrance to the nails. Then she took a second measurement. Oh, by the way, this is being done, you'll notice, in the naos side. The naos is on the east side of the Parthenon. And since we're measuring the solar year, the sun rises in the east. And the area she's chosen are areas from the eastern part of the temple. And here, the second measurement is right around the statue of Athena, right around the railing of the statue of Athena, right straight to the stylobate. And she came up with this value. Then what she did was to average the two. Came up with this value. And then added this to the day units for the stylobate, and came up with this value, which is very impressive for the length of the solar year. The accepted value is this. She did the same thing, by the way, for the lunar year. But to do the lunar year, she has to take values on the western side of the Parthenon. And I'm not going to show you that. It's a similar calculation. And again, she came up spot on for the length of the lunar year. Now, here's another way in which, in ancient Vedic times, the lunar year was measured. They took 10,800. You'll notice that that 108 number keeps coming up. That's the number of muhurtas in a lunar year, where one muhurta turns out to equal 48 minutes. So that measures the number of minutes in a Parthenon year. Now, the lunar year is measured in 360 tithis. So what I did was to divide the number of minutes in a lunar year by the number of minutes in a day to find out, this turns out to be exactly 360. And in the Parthenon, it appears here. If I take the stylobate and divide it into 9 similar stylobates, and there is 9 areas of equal areas, which have the same proportions as the original. Here. Turns out that the area of this is exactly 10,800 times 48. So either this is a fortunate coincidence, or there is something going on here. And so it's recapitulated in the Parthenon. Here's snapshot number 6. This is the Kappraff city chariot wheel of Vedic origin, and I'd like to show its connection to the Parthenon. Okay, here's an artist's conception of the Kappraff city. In fact, I took a look on the web last week and found the exact information on the construction of this wheel. However, there are no pictures. And this is an artist's conception of it. It's not drawn to scale, and there are some slight inaccuracies. But this gives you a general idea of what the wheel looks like. There's a rim with 145 bricks, at least according to the Subha Sutra. There are spokes which have 64 bricks. There are 16 spokes, each with four bricks. Each of the bricks has the same area, although that's not clear from this diagram. The center has 16 bricks. This shows only 8 of them. But there are 16, all of the same area. And then these little empty places here are exactly congruent to the spokes. And so if I add the built area of 145, 64, and 16, I get exactly 225 bricks for the built area. Now there were 64 empty spokes. If I filled them up and added them to the built area, I would get 289 bricks. Now, 225 equals 289 minus 64. And 289 is 17 squared. 64, of course, is 8 squared. So we have this Pythagorean triple coming up in the Kappraff city, chariot wheel. Let's take a look for a moment at the statistics of this Pythagorean triple. Well, the perimeter is 40. Well, to me, that looks like the length of the triglyph. The area is 60. That looks like the length of the mediphy. It's based on 3. The radius is 3. That's the musical aspect. And I even wonder, I even wonder whether the fact that 17 and 8 might even correspond to the number of columns in the east and west and north and south. Anyway, it's a very good number for the Parthenon. Now, the Sluba Sutra was a book of geometry, and here are four geometrical questions addressed by the Sluba Sutra. First of all, given a rectangle, can you construct a square of the same area? I showed that, by the way, in the Parthenon just before. Given two squares, can you construct a square that has area equal to the sum or difference of the two? And this is a generalization of the Pythagorean theorem. Then, given a circle, can you construct a square with the same area? That's called squaring the circle. And we know that you can't do this with compass and straight edge, but you can do it to within about 1.5%. And the Indians did that. Can you construct a ratio of integers that approximates the square root of 2? So let's take a look. Well, here's the first step. The chariot wheel measured, when you filled in all the bricks, 289 bricks. That can be is equal to 17 times 7. If you square the circle, you get 17 times 17. Here's a Pythagorean triple, once again. And now we want to focus on the area 225, which is the built area of that chariot wheel. And if I construct a rectangle with the same area as that square, I get the following rectangle, which if I magnify it by a factor of 140, I end up exactly with the length and width of the stylobate. So the stylobate fits in here perfectly. So beginning with the chariot wheel, I can end up with the Parthenon. And furthermore, one day I figured, well, let's see what happens if you took the area of the stylobate and divided it by those 225 bricks of the built chariot wheel. How much would what would be the size of the brick? Well, it turned out to be 144. The length of the brick turned out to be exactly 144. You can't make this up. I could have gotten 129.5. I ended up with exactly with 144. And 144 is the second big number that turns out from this analysis. And here is what the Parthenon would look like if I used 144 as the unit. The stylobate would now be 225 square bricks. The Scylla would turn out to be exactly 100. Very nice number. Oh, by the way, 120 and 144 also come up in the Bible, and music. Rising and falling Dorian mode, ancient Dorian mode. In a double octave, turns out to be 120 comes here, and 144 turns out to be here. And the Bible, there are 120 David singers and 280 priests who were trumpeters from the Bible, music and architecture, all together. Snapshot number 7 is the radius of the Earth from Parthenon proportions. Okay, now this is a work in progress. But I can show you one interesting result here. 1440 is the width of the Parthenon, and I made a square out of this and took took the number 1440 over and over again. One unit. I would take 1440, multiply it by itself. 1440 times 1440. And if that is the number of bricks, each brick is 144 dactyls. Well, the radius of the Earth turns out to be very close to this number. 1440 times 1440 times 144 dactyls. And if I convert it from dactyls to kilometers, I end up with 6,400 kilometers. Accepted value is 6371. Here's another way to get that number. Just take the volume of the Parthenon, the height, the width, and the length, and make a whole bunch of rods out of them, one dactyl by one dactyl, and then stack them up. It turns out to be exactly 10 times the radius of the Earth. Exactly. The same number as I got before, but multiplied by 10. Actually, I did. The circumference of the Earth comes in here, but I'd like to not talk about that right now. Sorry about that. That's nothing. I'd like to end up by mentioning that chariot wheel again, but to approximate the square root of 2. To approximate the square root of 2. I'll take the chariot wheel and first consider the rim. The rim has 145 bricks. The inner, this has 144 bricks to fill in the inside. So the rim of 145, the center of 144, gives me 144 plus 144 plus 1 equals 289. And that is 12 squared plus 12 squared is approximately 17 squared. With a little bit of arithmetic, you can see that you get the square root of 2 approximation of 17 twelfths. Right from the Rathatakra chariot wheel. And once again, you can look at it geometrically, with starting with 289 and breaking it down into 144 plus the rim of 145, squaring the circle, taking this rectangle and making it into a square, 2 such squares, gives the error of the approximation, leading right to the square root of 2. This is the slide I was looking for. This indicates that if I took the radius of 6,400 kilometers and multiplied it by what was considered an ancient approximation for pi, I end up with exactly 40,000 kilometers. 40,000 kilometers is a very good approximation to the circumference of the Earth, but actually, even more so, Napoleon is often held responsible for coming up with the measure of the meter. And the way Napoleon developed the measure of the meter, he took the arc from the North Pole to the equator, the arc of the Earth, from the North Pole to the equator, and divided that length into 10 million parts. Each part was defined to be a meter. That's where the meter came from. It was 1/10,000,000th of the arc from the North Pole to the equator. If I multiply that by 4, I get 40 instead of, I get 40,000 kilometers. So it's very possible that, and we feel that this is true, that in time of classical Greece, there was some, they may have come upon the millimeter in almost the same way in which they came upon it later on. Okay, so this, I believe, is, here is square roots of 2 come from something known as the Pell series, also a very ancient series of numbers. You'll notice that I multiply the number in the series by 2 and add the previous one, multiply by 2 and add the previous one, I get a sequence of numbers here. It's called a Pell series. If I did the same with 3, double 3, add 1. Double 7, add 3. I get another Pell series. The ratio of these two give me all the different proportions for the square root of 2. By the way, 3 to 2, musical fifth, actually, is the second in the Pell series. The fourth is the 17/12. This one gives me the square root of 2 to 5 decimal places. And apparently, apparently this was 577 over 408, was well known in ancient Vedic times. In fact, the Subha Sutra talks about this ratio to the square root of 2 and gives a compass and straight edge construction of it. Okay, I think this is what I would say called the end of the talk. And so perhaps we can have any questions. Oh, by the way, I should say that a little concluding remark I have here. I wrote down last night that so the study of ancient architecture brings together architecture, geometry, astronomy, music, and also biology, since these rhythms these occur not just in the solar system level, but in biological systems, marine animals, and cicada rhythms, and so all of these are encoded not just in the architecture but also in biology. Okay.
So, flip yours on.
Yes.
Okay. Did you also mention that music comes in here?
Music, definitely.
Most definitely. Okay. Let's take about 5 minutes or so for questions. We're running a little late into the lunch hour. If you raise your, okay. Let's see. So could you pass?
Fascinating talk. Do you think there's something common underlying all these correlations, visual correlations, the architectural and auditory correlations, music and so on, in that it's happening in our head, and there's a common process going on here. It could be wave. Wave is connected to numbers. And so all these correlations that you see in numbers, I wonder if underlying that is a correlation of waves in our head. electromechanical, electromagnetic, and concentration, chemical concentration waves, and mechanical waves, and so on.
Well, actually, I think it's very interesting. I would think that music would be a very good element to bring this out. Music is based on vibrations, and in fact, all these ancient cultures were oral cultures rather than visual, and they saw things through music, I believe, first. And what you say is very interesting. Worth exploring.
Okay, can you flip over?
Yeah.
Other questions?
Yes, Jay, perhaps you know that recently I published a paper where I showed that the pyramid in front of the Louvre has 666 glass panels, and that the cube in front of the similar museum in Brussels has 216 panels, and 216 is 6 times 6 times 6. So I entitled my paper "The Diabolic Connection Between Brussels and Paris." Unfortunately, this paper appeared just on the moment of the bomb attacks in Paris, which were prepared in Brussels. Why am I saying this? I discovered this 666 in the panels in the pyramid and the panels in the Louvre, but I did it like a humoristic. I published it as a humoristic paper to illustrate numberism. So I'm not surprised, in contrast to my Japanese colleague there, I'm not surprised that if you start with the numbers 2 and 3, and if you juggle a little bit, then you come up with whatever numbers. This afternoon I will start my talk showing that the distance from Vienna to the birthplace of Leonardo da Vinci and the distance of Vienna to the place where he died are also correlated by a factor of 1.3. So give me some numbers, I will find you a relation. To be honest, during your talk, very often you use the expression "are almost exactly." Almost exactly? It's almost or it's exact. Of course I know what you mean, Jay. I know your work. I know your work for a long time. Please don't misunderstand me. I know your excellent work. This is not what I wanted to say, but this, for me, goes a little bit too far.
Okay, I admit that all of this could be just some marvelous coincidences. However, there are very curious kinds of coincidences because there are, first of all, so many of them, and almost any time I try to divide two numbers together, I would get something which appeared to be quite significant. And so it could very well be a tremendous confluence of coincidences.
Yes, but sometimes I know that here, sometimes you say, if I multiply by 4, then I get this.
Oh, no.
So why don't you multiply by 5 or by
Well,
7?
no. I was very clear about the fact that everything that I'm talking about, since everything is first of all based on music, and any number can be equivalent to its double or any power of 2. So I chose power of 2 only to multiply things by, because that gives you a tone in exactly the same tone. It's almost like an identity. So I would never multiply by something else. Yes.
Okay. Any brief question? Okay. Brief question. Oh boy, I have to get this all the way over. Okay.
Thank you. There is, from your talk, there is no doubt that the Greeks and all the civilization were fascinated by numbers to build or the Parthenon and other things to interpret the time and so on. It seems that number 2, square root of 2, is important in this context. And later, Le Corbusier was fascinated by number square root of 5 minus 1 over 2. Okay. And my question is, it turns out that the worst quadratic irrationalities that are square root of 5 minus 1 over 2, the golden ratio, and square root of 2 minus 1, which is about the ratio on an A4 of length, and on a ratio, that is a ratio on an A4 paper also. These two numbers are the difficult to approximate, the worst to approximate in terms of rational numbers. And it seems to me strange that square root of 2 is important for the Greeks and other civilizations, and later came the golden ratio, like in Le Corbusier and other people. And why the Greeks and other civilizations didn't use the golden ratio?
But, sir, it's not true that Le Corbusier, what you said about Le Corbusier and the golden section, it's very debatable. Really? Yes, I'm sorry.
Let's not have a debate.
Yeah, I should mention one last thing, is that you must
Hello again.
realize by now that I did not mention the golden mean once during this presentation. And that there's a lot of folklore that the Parthenon is very closely connected with the golden mean, and we did not find this. It is connected only if your tolerances became something on the order of 2%. But our tolerances were set at a level of about 0.02%. And so, in that sense, the Parthenon, the golden mean just misses. It's not caught in the neck. Okay.
Thank you.
Okay, first I'd like to thank Jay for a very interesting talk, and second I would like to say that the lunch break is from now until 2 o'clock, or translated 14 hours. So let's thank Jay Kappraff for a very interesting talk. So we return here then after lunch.